Hey there, ladies and gents. Let's go ahead and talk a little bit about slopes, parallel and perpendicular slopes, and how you can tell just by looking at the slopes that you're dealing with something that's parallel or perpendicular. So there's going to be a couple ways to do this, but the first thing we have to talk about is slope itself. Now, this is not a new concept for us, of course. When we're talking about slope, we're simply talking about how steep something is, like how steep is that line, or how steep is this line. And it's something that you guys calculated probably since 7th or 8th grade, so certainly this is like year 4 of slope. So hopefully this is just a little bit of a reminder for you. Um, so when you're looking at slope, there's a couple different ways you can tell what the slope of a line is, how steep a line is. The first way is just going to be able to look at excuse me, just be able to look at the equation and just tell. Which means that you're given a linear equation probably in one of two forms. The first one being the slope-intercept form, the y equals mx plus b that I'm sure we're all familiar with. And the second one being what we call point slope form, which is y minus y1 equals m, which is of course a slope, times x minus x1. It's one that you would have seen in Algebra 1, probably use it a whole lot less than this y equals mx plus b. And so whenever you're given an equation like this, all you have to do is to know where to look for the slope and just pull that number out of the equation. Typically, slope is going to be identified using the letter m. If you look at both these forms side by side, all we have to do is find where that m is, and then we have the slope of the line that we need. For example, just throw a couple examples down here. Let's say we have like y equals negative 3 over 2x plus 1. Well, if you note, the slope is going to be the number right in front of the x, the coefficient of x. The slope in this case is just going to be this negative 3 halves. And so this tells us that the slope, which will be represented by m, is just going to be negative 3 halves. Okay? And so when you're given the equation, it's just a matter of looking, knowing where to look. And of course, in this case, it's always going to be the coefficient or number in front of the x. And you'll always get your slope. Even if I decide to try to, someone trying to trick you a little bit, and they write the equation in a way that's not exactly aligned to y equals mx plus b, that doesn't change where you look. You're still always going to look for the number that appears in front of the x, the coefficient of x. And so like in this case, the slope is just going to be positive 2, or expressed as a fraction 2 over 1. It's typical to express slope as a fraction, even as a whole number, throwing it over 1. So we get our whole slope value so we can kind of tell our rise and run. Over on the right-hand side, we're going to see very similar things, except this form is slightly different. That doesn't change where we're looking, as long as we can identify that the slope is going to be this number in front of the parentheses of this form of the equation. We should be able to pull slope really fast. And so let's say I have this equation like y minus 5 is the same as 2/5 x plus 1. Well, the number that appears in front of the parentheses with the x in it is going to be our slope, and so we can tell right away that our slope in this case is going to be 2/5. And that's how steep that line would be. Okay? Again, another example is say we have y plus 1, then we have here equals 2, let's say make it a negative 2, x plus 6. Okay? Again, just knowing where to look, the number in front of that parentheses will tell us our slope, in this case is going to be negative 2. Or if we want to do it so it's a little more useful for us, negative 2 over 1. So that's the way we can tell what our slopes are going to be. Now, you're not always going to be this lucky that we just give you an equation and then you have to pull that number out of that equation, because certainly in this form it's going to be fairly easy as long as you know where to look. Most likely you're going to have to calculate it. Now, calculate is not a big deal as long as, again, you know where the pieces are coming from. This is probably the most typical version of the slope equation. Here we're taking a subtraction problem of y2 minus y1 and putting that over x2 minus x1. So it's important to note that these y2s, x2s, y1s, x1s, which we've dealt with before, say like in the distance formula, just represent points on the coordinate grid. And so this x2, y2 simply refer to like this point on the coordinate grid, which is going to be like that point, excuse me, like the end point of the segment. And then this y1, x1 business, again, just refers to a point. In this case, it's going to be like the other end point of the segment, or at least where we're going to be taking our slope. Okay? And so all we have to do here is do a calculation, y2 minus y1, x2 minus x1, and we're going to have our slopes. And so again, it's important to note that these just represent points. Okay? Another way to look at slope, besides its like formal calculation, is probably rise over run. That's probably again the most typical way you would have like maybe remembered how to get slope. And a slightly more formal version of rise over run is delta y over delta x, where delta y just means the overall change in y, and delta x just means the overall change in x. So change in y over change in x. That's really all that delta means, is just a change. So like when you're looking at this representation, this kind of combines all the stuff that maybe you're familiar with slope. Certainly we have the calculations x2 minus x1, y2 minus y1, but those just calculate the rise and the run, which is a translation of how much you move over and then how much you move up. And so these are all different ways to think about slope. So let's put some into action right away. And so let's say I wanted to calculate the slope of this line. So it looks like I picked out two really nice points that appear on the grid line. And so again, I kind of have some choices. I can look at it in terms of the calculation. I can think of it as rise over run or just change in y over change in x. Being on the grid, it seems like maybe the most natural way to do it is just to pull a rise in the run, change in y over change in x. So my change in y, my delta y, my rise in this case, this is going to be 1, 2, 3, 4, so it's going to be plus 4. And then my run, or my delta x, my change in x, is going to be plus 1, 2, 3. So as far as my slope goes, we're just going to take change in y over change in x, the rise over the run, and so this is going to be 4/3. Okay. We certainly could have calculated it since we do have the points here as well, but counting it on a grid seems just as easy. All right. So here's another example. We have a line. We don't have a picture of it, but we do have these points that it passes through. So we probably do ourselves a favor here and label these x1, y1, and of course x2, y2, just so we have something to reflect or pull into our slope formula, which I'll write here first. So a slope is going to be change in y over change in x. But that's going to be the same as that y2 minus y1 calculation over x2 minus x1. Okay? And so it might take a second here and just kind of make sure we know where all the pieces are coming from. So y2 is going to be that y2, which is going to be this 5. The y1 is going to be the y1, so that's going to be 8. The x2 is going to be this guy right here, so it's going to be 7. Okay. The x1 is going to be this guy, which is going to be 9. And so pulling those values out of my my points I've been given, I should have, let's see, 5 subtract 8, my first one. And on the bottom, x2 minus x1 is going to be 7 subtract 9. Now it is important that we keep the order the same top and bottom, so whichever we're identifying as the first point and the second point, the x1 and the y1 need to come from the same point set, and the x2 and the y2 have to come from the same point set. And so carrying through a calculation, we have 5 subtract 8, that's going to be a negative 3. 7 subtract 9, that's going to be a negative 2. Two negatives, of course, make a positive, and so we'll end up with a slope of 3 over 2. And so just as fast as counting on the grid, we can do this calculation. It's one that you could potentially make some errors because we're dealing with some negatives, but not one that we couldn't overcome with a little bit of practice. So here we have actually the same kind of problem, but just with different numbers. So we're dealing with delta y over delta x, which is our rise over run. So this will be, let's see, y2 minus y1 over x2 minus x1. So I'll label this really quick. That'll be x1, that'll be y1, that'll be x2, that'll be y2. So this is kind of like our first point. This is like our second point. And so y2 over y1, well, that's going to be our y2 minus y1 will be, see, 4 minus 2. And on the bottom, we have x2 minus x1, so that's going to be 7 subtract negative 3. Please note in this one that there actually are two minus signs. One comes from the value of negative 3, but also one's carried in the formula. So we do have two negatives there. It's a common mistake for people to drop one of those negatives. You guys won't do that, but just know that that's one of the more common mistakes when you're calculating slope. So on the top, we have 4 minus 2, which will leave us with just a 2. On the bottom, we have 7, and this will, of course, be plus now. 7 plus 3, which is 10. So our slope is going to be 2 over 10, but we'll reduce this to 1/5. because we can take a 2 out of both, leaving 5 on the bottom, and our slope is going to be 1/5. And so slope calculation, again, can be done a lot of ways. With a graph, it seems like it's easiest to count. If you just give it a bunch of points, well, you're going to have to calculate those, right? So that's slope. So part of understanding like parallel and perpendicular slopes, hope you're getting the impression that calculation of slope is really important, because in the end, if you want to know that lines are parallel and perpendicular, you're going to have to know about their slopes. Um, if you consider the graphs of parallel and perpendicular, over here, of course, being parallel, okay? If you observe these lines and you think about how they move, well, of course, we know that parallel means that they're never going to intersect because they're the same distance apart. But the reason they're the same distance apart is because they're changing by the same amount. So parallel lines, we're going to say change by the same amount. We say change the same way. Okay? And so as you're moving along the x in either direction, both the lines are increasing or decreasing by the same amount. If you contrast that with perpendicular, and perpendicular here is where you have this right angle, they're not changing by the same amount. In fact, they seem to be the exact opposites of one another. And so when we look at perpendicular, the operative phrase here is exact opposites. Okay? What I mean is this, and you can kind of see the triangles, or the slope triangles already being kind of counted in here. And so if you look at the line that's moving upwards, we see this triangle here where we're going to be moving up 3 as we move forward 4. And so that gives us a slope of just 3/4. If you look at the one that's perpendicular to it, it's moving very differently. It's actually moving down 4 as it moves over 3. And so the slope for this guy is going to be down 4, which would be -4, over 3. And this is what I mean by exact opposites. If you look at these two slopes, uh, you look at the one slope being, say, 3/4, and the perpendicular sign, don't forget about that. The perpendicular slope is -4 over 3. These couldn't be more opposite. One is positive, one is negative. And then we also see that there's a flip-flopping, there's a switching going on here. And so the 4/3 and the -4/3 are flip-flopped. Now there's a term for that. So we have this, these lines are perpendicular if and only if they behave exactly like this. Well, that behavior is called opposite reciprocation. And so we have that lines are parallel if and only if the slopes are identical, or the same. And the lines are perpendicular if and only if the slopes are opposite reciprocals. Okay, and that's what opposite reciprocals mean. The term opposite reciprocals means two things are true. One thing is true is that the fractions have flipped. Okay, and the other thing that's true is that the sign changed. In other words, positive, negative. And so if you look at these slopes up here, one is positive, one is negative, and the fractions flipped top to bottom. And that's what's meant by opposite reciprocals. So those are the actual rules for parallel and perpendicular slopes. And so if you have them that are the same, you know they're parallel. If you know they're opposite reciprocals, that means that they're going to be perpendicular. Now, the thing that's interesting here is if it doesn't fit either one of those two categories, we can just say they intersect. So either they're going to be parallel, they're going to be perpendicular, or they just happen to cross. Right? So this is where I'm going to end the first video. The next video is going to go through the examples below. Thank you.